Okay, that's better. Okay, how are we doing? Anybody taking the practice test this week? How's your scores doing?
50s.
50s? Okay, you're just about right on schedule. We're halfway through the course now. So if you're in the high 40s or early 50s, you're doing good.
Dale, are the tests set up to where if you score high in a certain area, you don't get that many of those questions? I'm kind of looking at mine and it's kind of like all over the board, anywhere from 40 to 72.
No, that's pretty much the way it is. It's just all over the board. They don't really base it on how you've done so far. It's kind of a random selection, but they have a certain number of questions from certain categories. So it makes sure that every test, covers all the different categories.
Okay, so then my lack of knowledge on antennas isn't going to kill me then. Thank you.
No, probably not. No, all you have to do is get about a seven, or you have to get a 75% to pass the test. Okay, anybody else? How you doing on your test? Okay, well, I'd like to encourage you to keep doing the practice tests. The more you do those, the better you're going to be. In fact, when I took my test, that was all I did. I just went through the practice tests a few times and went and took the test. So, yeah, keep trying, and don't feel bad if you don't get a real high score yet, because we're only halfway through the class. Okay, any questions or things from last week or the previous weeks? Okay, well, we'll go ahead and let's get it started. Actually, tonight should be kind of a fun one.
No more math.
No, actually, I think we're done with the math. So now we're going to get into the more fun stuff. There you go. Can you see that okay? There we
At like India somewhere. I've seen Indian wiring like that.
go. Well, like I've mentioned before, this is the kind of hobby you can spend as much money as you want to. I just come across this picture one time and I thought it was kind of cute.
Kind of reminds me
Somebody
of
hijacked Radio Shack.
Yeah.
Incident Command for firefighting.
Yep. Well, oops.
That it's like a guy that has 20 wristwatches on his wrist and he's out selling them. While this
Yeah.
guy stole a bunch of radios.
I don't know if he's selling them or not. I don't know what he's doing with them. I don't know. I'd get lost. I don't know how you keep track of that many of them. Well, here's the outside view of it. Got to have antennas for all of them. There are some guys that get a little carried away with some of this stuff. Okay.
Does he wear a tinfoil hat?
He probably does. I didn't see the driver. Probably with the little whirly bird on top. Okay, tonight I'm going to show you how your radio works. So how is it that when I push this button and talk into this microphone, somebody clear on the other side of the county can hear me? How does it do that? So I'm going to show you the kind of the basic technology of how a radio works and explain some of the parts of it tonight. There's not a lot on the test about this, but there are some questions, and I'll kind of show you what they are. Okay, the radios that we use, we refer to them as a transceiver. And the reason we call it that is because it has a transmitter and a receiver in it. And the transmitter and the receiver are separate circuits. Years ago, back in the early days of vacuum tubes and stuff, the transmitter and the receiver were two separate units. You had a box sitting on your desk with it was the transmitter, and it had another box that was the receiver. And you had a switch where you could switch back and forth between the transmitter and the receiver. In today's world, it's much more compact than that. But inside your radio, there are two separate circuits. One's the transmitter and one's the receiver. So in the normal mode, the receiver is powered on and the transmitter is powered off. And so all you're going to do is just receive. But when you push the button, the press to talk button, that will turn the receiver off and turn the transmitter on. So then you can talk and it will transmit over the antenna. So I'm going to go through several different types of radios and show you how the transmitter works and show you how the receiver works, because they're totally separate circuits. Now, if you remember back when we, one of the earlier classes, we talked about transistors and components and stuff. Well, we can actually take a circuit and make it into a block diagram. Or actually, probably start with a block diagram, then make it into a circuit. But we take, like this first transistor here, so there's a transistor and some components associated with it. Okay, we can make that a block. Now, this is just for explanation purposes is all. It doesn't actually exist that way. We can label this block and we say, okay, this is the preamp. This is the first amplifier of this circuit. Then we have the second block, and again, it's a transistor with some associated components. And this would be the main amplifier here. And then we have another block over here, which is another transistor and some components. And this we would call the final amplifier. So we can put these blocks together and cause the circuit will flow from one circuit, or I mean the signal will flow from one circuit to the next. So in this explanation tonight, I'm going to show you the blocks of the transmitter and the receiver and how they work. Okay. So first thing I want to talk about is called an oscillator. An oscillator is what creates a frequency, and it can be an audio frequency or an RF frequency or some kind of a frequency, but this oscillator is what creates that. So I'm going to do a little demonstration here and show you how an oscillator works. And let's see. Push that button. I have to switch back and forth because if I put the video inside the PowerPoint presentation, the video just doesn't come out very good, so I have to do them separately. Okay, so I'm going to bring up this one. There we go. Okay, can you see that okay? Oops. There, get that out of the way. Okay, so here's a little demo here to kind of show you how an oscillator works.
Okay, for this demonstration, I'm going to show you how we make an oscillator. An oscillator is what actually generates the frequency. That's how a radio makes the frequency that goes out over the air. So what I have here is this is a little PA system. Test, test, 1, 2, 3. And you know what happens if you put a microphone in front of a PA system? You get that feedback. Well, that's actually an oscillator. We're actually creating a frequency by doing that. But the problem is we want an exact frequency. This is just a random whatever, wherever the microphone happens to be, that was what the frequency is going to be. So what we're going to do is this is a crystal glass. And if you know how to make it work, my fingers are too dry for it. But anyway, I'm going to put the crystal glass right in front of the speaker. I don't want it touching, but I want it very close. And then when we do the oscillation, the speaker is going to vibrate the glass, and then I'm going to put the microphone in front of the glass, so the glass will then vibrate the sound into the microphone. And we'll get a feedback, but it'll be controlled by the crystal. So let's see if we can make this work. A little too much. There we go, almost got it. Okay, there we are. Okay, so the crystal is actually creating the frequency that we're looking for. Just a little bit more here. There we go. Okay, so that's how we create make an oscillator. And inside the radio, we do the same thing, only we don't use we're not using a microphone and a speaker. We can actually use solid state circuitry to take the output of an amplifier, feed it through a crystal, and then feed it back into the input. So it will oscillate at a specific frequency. And if we wanted a higher frequency, we could probably get a smaller glass, and it would create a higher frequency for us on this feedback. Okay, now this is just an audio frequency here, but if we want to go up into the radio frequency, that crystal is going to have to get smaller and smaller and smaller. It's like that frequency and wavelength thing, as the crystal is actually, I mean, this is physically a wavelength for audio, and as we continue shrinking that wavelength down and down and down, the frequency is going to get higher and higher. And we can actually shrink it down to a little tiny thing here. Now, if you can see this is actually a crystal that I've opened up. Let me put my finger behind it there. Can you see that little round disc? Okay, that is a crystal. It's made the same material that this is made out of, and it's suspended by 2 wires, one on each side, and you can feed the signal in on one side, and it will vibrate the crystal, and then the output of the crystal will then feed back into the amplifier, and it creates a feedback, but it's at a very specific frequency. Now, I don't know if you can see, but right at the very top, there's a flat spot. If you can see that in there. Okay, that's how they tune a crystal. They get these crystal blanks that are, you know, about this size, and they put it in a machine, and they slowly shave the top of it until it gets to the frequency that they want. They actually hook it up into an oscillator, and they can measure the frequency, and they just very slowly take very, very thin slices out of the crystal until it gets down to the frequency they want, and then they stop. So that's how an actual crystal works. Most modern radios have at least 3 crystals in them, sometimes 4. They're used for, you're familiar with a computer, you know, you have to have a clock in the computer. Well, the radio has to have that too, because it has a microprocessor and has digital circuitry and so forth. So there's actually a clock frequency, and that's created by a crystal. There's also a crystal in the audio processor circuit, and then there's a crystal in the receiver mixer circuit. And later on, when we get into how a radio works, I'll show you where those crystals are located. But that's how we actually create a frequency. We just create a feedback, an amplifier, and feed it back through a crystal, and that controls the frequency. And these crystals are actually very accurate. Once they get burned in, after they've been aged for a little while, they're very, very stable, and they stay right on frequency, and very rarely do they ever drift. So let's go back to the classroom now, and we'll talk a little bit more about the radios and where these oscillators are used and what they're used for. So let's switch back over to that now.
Okay, so now we know what an oscillator is. We can go in and let's see where I'll show you how the rest of it all works. Okay, so remember I showed you earlier we were talking about this block diagram. Okay, this is a block here, and this is basically a 1-transistor amplifier. We have an input over here, and we have the output over here. But we're just representing it with a block because we don't want to draw all the components for it. So this is an oscillator. It creates a frequency, and it's going to send the frequency out here. So what we're going to do now is we're going to put in a crystal filter. That is represented by this here. So we're going to take the output of the oscillator, and we're going to feed it into this crystal, just like I showed you in the video, and then from the crystal back to the input of the amplifier. So it's actually going to go into oscillation, you know, just like when you put a microphone in front of a speaker, it's going to squeal. Well, this does the same thing, but the crystal controls that. So we call it a crystal controlled oscillator. And they've been used for many, many years, and they're still used in radios today. But the crystals have shrunk down quite a bit. They're much smaller than what they used to be. So, okay, and then this is just the frequency output, and we can do whatever we want with the frequency once we've created it. Okay, now in a radio, this is kind of the magic part of it, at least in the receiver. It's called a heterodyne circuit, or more commonly known as a mixer circuit. And a mixer has some very unique properties to it. We can put two frequencies into it. We're going to put frequency A and frequency B into this mixer. It's usually just a one transistor circuit. And the output is going to give us 6 frequencies. We're going to get frequency A and frequency B, and then we're going to get 2 times frequency A. In other words, it will double the frequency. We're also going to get 2 times frequency B. And we're also going to get the sum of A plus B. And we're also going to get the difference between A and B. So it's A minus B or B minus A. Okay, so in our circuitry here, the only thing we care about is that one right there, the A minus B, the difference between those 2 frequencies. And this can do some magic stuff for us. It's pretty amazing how it works. So, let me give you an example. Let's use CB channel 19. Okay, the frequency for CB channel 19 is 27.185 megahertz. Now this frequency B, we're going to create that frequency using a local oscillator, just like we showed earlier with that crystal controlled oscillator. So that oscillator is going to create a frequency of 26.730 megahertz. So if you take the difference between A and B, the output is 0.455 megahertz or 455 kilohertz. Okay, this is very significant. And I'm going to show you why here in just a little bit. So we use this all the time. Almost all radios use this technology now because it just works so good. Okay, so I'm going to look at a receiver. This is going to be an AM radio, like a CB radio or an HF radio or something. Okay, so on the front end, we have, this is the antenna here, this triangular shaped here. This is the antenna, and we're going to send it into a preamplifier. It's usually a one transistor circuit, and it's just going to amplify it so that we get a stronger signal. And then from there, oops, come on. There we go. Okay. So now we're going to send it into this mixer circuit or this heterodyne circuit that I just showed you. Okay, so we're going to have 2 inputs, and down here is going to be a local oscillator. Now this local oscillator, we can create it with a crystal, or I'm actually going to show you another way that we can synthetically create those frequencies. But somehow we're going to generate that frequency. And so this local oscillator right here is going to go into this mixer circuit, and anything that comes through the antenna is going to mix with it. And you may get hundreds of frequencies, whatever happens to be on the air at any given time. Usually with this preamp circuit, we put a bandpass filter because we don't want to have to deal with 10,000 frequencies. So we just want to narrow it down to, in this case, I'm using a CB channel. So the bandpass only allows the CB channels to go through. So everything else is filtered out. So that way the mixer's not trying to deal with all these hundreds and thousands of frequencies. So we go into this mixing circuit, this mixer circuit, and you remember that example that I showed you a little while ago? Okay, actually, I'm getting ahead of myself here. Okay, the output of the mixer circuit, we're going to pass it through a filter. And can you guess what the frequency of that filter is? Okay, so let's go back to our example here. We got 27.185 megahertz that's coming through the antenna, along with everything else that's out there. And then we're going to set this local oscillator to 26.730 megahertz. And remember we calculated earlier, the difference between those two frequencies is 455 kilohertz, which is 0.455 megahertz. So now we're going to put a filter right there that's only going to allow the 455 kilohertz to pass through. So once we get into this mixer circuit, we could have literally hundreds and hundreds of frequencies right here, but only this one right here mixed with this one is going to produce the 455 kilohertz. All the rest of these frequencies are going to be either higher or lower than that. So we're going to run it through this filter to only allow the 455 kilohertz to pass through. And then once that it goes through there, we have to use an amplifier because by the time you go through the mixer and the filter, the signal's pretty small. So we just need to amplify it, get it back up, where we can work with it. And then over here, now this is an AM circuit, remember, this is like a CB channel. And from there, it goes into what's called a detector. And a detector is what extracts the audio from the modulation. Remember, I think it was last week we talked about modulation, the AM modulation. Okay, this can actually detect that, and it's going to extract the audio and throw away all the RF because we don't need the RF anymore. All we're interested in is the audio. And then from there, it's going to go into an audio amp circuit because now it's actually audio. We're hearing the actual voice that came over the air. And then from there, in between here, this is where the volume control is. So we're going to control how much of that audio gets into the audio amplifier so we can determine how loud it's going to be. And then from there, it's going to connect to a speaker. So this is a very simplified diagram of how an AM circuit works. So but like I say, the magic part of it is this mixer right here. This is how we actually determine what frequency your radio is going to listen to. And it's controlled by this local oscillator. So if we want to change channels, what we do is change this oscillator frequency so that it mixes with a different frequency. So it no longer mixes with this, it mixes with something else to produce the 455 kilohertz. So every time you change channels, this is what you're changing. You're changing the frequency of this local oscillator. And that's how we're able to extract one frequency and reject all the others. Is through this heterodyne circuit, this mixer circuit. And like I say, these have been around for a very long time. These have been in, gosh, since way back in the vacuum tube days, even before voice modulation was available. And they work really well. They're very, very unique, but they work. Okay, now in an AM circuit, there's one extra factor that most other or FM doesn't have, because AM is amplitude modulated. So it's relying on the strength of the signal. It's modulating the power of the transmitter. So as you get farther and farther away from whoever you're talking to, the audio is going to get smaller and smaller. And as you get closer, it's going to get louder and louder. So if you're driving your car, or moving somewhere, your audio is going to fluctuate a lot from loud to soft. So to compensate for that, we put in a circuit right here. It's called an AGC. It's an automatic gain control. So it's measuring the strength of the signal that's coming through the amplifier, and it will adjust how much amplification that it does. So if the signal starts getting really strong, it'll back it down a little bit, turn it down so that it stays the same. And if the signal starts getting weak, it will increase it. It will increase the gain. So by the time it gets to the mixer, it's usually fairly stable as far as the strength of the signal. It keeps it pretty constant. So that way our audio doesn't fluctuate, at least not too much anyway. So that's basically how the receiver for an AM radio works. And these are actually very simple. You can build this out of coat hanger wires and duct tape. A lot of people used to do that. Get some wire, wrap it around an old box or something, and put a crystal on it, and get a crystal filter, and it works pretty good. Okay, so now I'm going to look at the transmitter for an AM radio. Okay, so the transmitter, we're going to start with this oscillator, and we're going to use, in this case, we're going to use a crystal to control the oscillator so that it's producing the exact frequency that we want to transmit on. Okay, and from there, it goes into an RF amplifier because this oscillator is actually producing the frequency that we're going to transmit over the air. So we don't have to do anything to it other than just amplify it, make it stronger. And then from there, it's going to go into another amplifier. And from there, it's going to go into another amplifier. And from there, it's going to go into another amplifier. We'll call this the final amplifier. And we can amplify it as much as we want, to get however much power we want. And then in addition to that, down here, we're going to have a microphone. Okay, so we're going to transmit on this microphone, and it's going to go into an audio amplifier. And then that's going to go into another audio amplifier. And that's going to go into another audio amplifier. And then it's going to go into another audio amplifier. So by the time we get to here, the amount of power that's coming out here is about the same amount of power that we have here. So in this case, you have to amplify the audio quite a bit to get it up, equal in power. And then from there, we're going to send the audio amplifier into the final amplifier. And that's where it's going to modulate create the amplitude modulation. And this is one reason why you're told never to put a linear amplifier on a CB radio, because once it's modulated, you should not amplify it anymore. And the reason for that is the linear amplifier is going to create all kinds of spurious emissions, and you're going to wipe out every radio in the whole city, and street lights and cameras and everything else because of all these spurious emissions. So in an AM radio, you should never amplify it once it's been modulated. So if you want more power, then you have to get something with more amplifiers in it to get the power up. CB radio is typically about 3 to 5 watts. And so you're going to have about that much power here, and you're going to have about 3 to 5 watts in audio, and you mix it, and you're going to come out with about 3 to 5 watts coming out to the antenna. But if you want more power than that, then you get one that has more amplifiers in it, and you can amplify it to 30, 40, 50, 100 watts, even 1,000 watts. But you can't do it after it's been modulated. You have to do it before. Okay, and then once it's been modulated, then from there, it just goes right to the antenna. And we broadcast it out over the air. So an AM radio is really very simple. They're simple to build, and years ago, people used to build their own radios all the time. But FM radios are a little different. They're not so simple. Okay, so now we're going to look at the receiver of an FM radio. As soon as I get rid of this thing again. There we go. Okay, so an FM radio, this is a frequency modulated radio, is actually, in some ways, there's some parts that are the same, but some parts are very different. So again, we're going to start out with an antenna, and we're going to go through a preamp. The preamp is just going to give it more sensitivity, be able to pick up a smaller signal. And then from there, we're going to go into the mixer circuit, which is that heterodyne circuit that I told you about. And this part is just like the AM radio. We're going to have a local oscillator. This is going to create a frequency that's going to mix with whatever's coming in the antenna. And then it's going to go into a filter. We call this the IF filter. It's an intermediate frequency filter. But this is where it gets different. Now we're going to do it at 10.7 megahertz. And it's not because it's FM versus AM, but it's because it's in a higher frequency band. Usually the AM radios are usually all in the low frequency bands. I call them low band. But the FM is usually up in the higher bands. So let's give an example here. Let's pick a ham radio frequency of 146.980 megahertz. And then the local oscillator, we're going to make it oscillate at 136.28 megahertz. And if you do the math there, you take the difference between the 146.98 and the 136.28, the difference is 10.7 megahertz. So we're going to mix, and this mixer is going to mix with all the frequencies that are out there, and it's going to create hundreds and hundreds of frequencies at the filter, but only that combination right there is the only thing that's going to produce the 10.7 megahertz, which is then going to go through this filter. So we're going to get rid of all the other stuff and just leave the 10.7 megahertz and let it go through. And so from there, we're going to put it into an amplifier. This is another IF amplifier, just like the AM radio. And then from there, now this is where it gets really different. We're going to put in a second mixer circuit, a second heterodyne circuit. So we're going to bring in another local oscillator, and we're going to mix it again. This time, the second local oscillator is always, oops. Okay, it's a little later. But anyway, we're going to mix it again. And this time we're going to put it through a different IF filter. We call this the low IF filter. So the ones up front, that's the high IF, and the ones down lower, it's the low IF. And the low IF filter is going to be 455 kilohertz, just like it was in the AM radio. So in the FM radio, we're actually doing a two-step. We're going through a mixer here, amplify it, and then go through another mixer here, and then we're going to amplify it again. Okay, now this mixer is always 10.245 megahertz because this IF up here never changes. It's always 10.7. So we mix 10.7 with 10.245, comes out at 0.455 megahertz or 455 kilohertz. So you're thinking, well, wait a minute, why are we mixing it twice? Why don't we just do it right the first time? Well, the reason for that is that scientists have learned that by doing a two-stage like this, we get better selectivity, and selectivity is the ability to listen to one frequency and reject all the others. And it also creates better sensitivity. So it's able to pick up weaker and smaller signals. So they do it in a two-stage, which improves that. And some of the really high frequencies, like when you get up into microwave and up into cellular and stuff, they actually do 3 stages. They mix it 3 times. And again, it's to get better sensitivity and better selectivity. So once we get through the second IF, the low IF filter, it's 455 kilohertz. Now we're going to put it into another low IF amplifier, or I mean low IF. Oh, I'm sorry. Okay, this is the low IF filter. Okay, right here is where we're filtering it. And then here we're going to amplify it again. Because once again, once you go through the mixer and the filter, the signal gets pretty small. So we have to amplify it again to get back up where we need it. Excuse me. Now from here, I had to drop down because my page wasn't wide enough. So in an FM radio, it now goes into what's called a discriminator. And a discriminator is, once again, that's where we're taking the audio and we're extracting it out of the modulation. So that once we come out, we take this 455 kilohertz, which has the voice modulation on it, and then go through the discriminator. And the only thing we're going to get out is the audio. So from there, we go through a volume control and we go into the audio amplifier. Okay, so an FM circuit's a little more complex, has more parts to it. And this is just a block diagram. You know, there's all kinds of other little things going on in there too. And then the audio amplifier then goes into the speaker. So that's how we can receive on an FM circuit.
So, Dale, is the volume control, is that like a variable resistor?
Yes, that's what it is. It's a variable resistor. So we can adjust the amount of resistance to adjust the amount of audio that goes in.
One thing Gordy explained really well when I took a class from him a few
Uh-huh.
years ago. He talked about the oscillator via, VFO, variable frequency oscillator, which is really just a dial for changing channels or changing
Yep.
frequencies on your radio. So that was like an aha moment for me. So it simplified it.
Yep. Yep. And a VFO is, well, you put it in your radio in the VFO mode. And basically what it does is it allows you to manually adjust this frequency here. So that's how you tune your radio. You can, in fact, the old radios years ago had a dial on them, and you use this dial to change this frequency here. And that's going to change what you receive through the mixer. And so that's what you're doing. And you go into that VFO mode on your radio, you're just manually adjusting this frequency here so that you can pick up something different or whatever you want to pick up.
So that would be your 128 frequencies on your Bofang.
Yeah. Mm-hmm. Yep. And actually, I'm going to show you how we do, rather than having 128 crystals in there, we can actually do it. We can synthesize the frequencies, and I'm going to show you in a minute how that does that. Okay, so now let's look at an FM transmitter. Okay, and once again, just like the AM radio, we start with an oscillator, and this oscillator is going to create the frequency that we're going to transmit over the air. Okay, from there, it goes through a phase modulator. If you remember back when we talked about FM modulation, you can have direct modulation or you can have phase modulation. And I'm going to explain just a little bit what the difference is. Okay, from there, it goes through an amplifier. And this part's really simple. It goes through another amplifier, another amplifier, another amplifier, and out to the antenna. That's all there is to it. It's quite simple in theory. Because right here is where we're injecting the audio. This is where we're modulating it. And then from there, you can amplify it and it goes right out the antenna. Now, an FM radio, you can put a linear amplifier on it and they work okay. You can amplify it, take out of the radio and put it into an amplifier and get more power out of it. And FM is okay because there's no modulation at the power amp. Okay, now, along with the FM radio, we have what's called signaling, and most of your radios have like a keypad on front. You can actually send DTMF, that's a touch tone. You can send that over the air. You can also have the PL tones. If you're familiar with that, it's a tone that we use for signaling, for controlling the radio. And there's various other signaling things that we can put into the radio. And all of those go into what's called direct modulation. We take all of the signaling here, whatever we're using, and we feed it right into the oscillator, and it modulates right there in the oscillator. So it actually produces FM modulation coming right out of here. But then if we're going to use a microphone, okay, this is our microphone right here. Now the microphone, actually there's a couple of stages of amplification, but microphone feeds into the phase modulator. So we're actually modulating the signal in two different places for two different methods. And the reason we do that is you can theoretically mix this and the microphone together and modulate it all at the same time, but it's a lot cleaner. It's a lot easier to do if you put the signaling in here and put the microphone out here. That way you can control these separately. You can adjust the signal of this, and you can adjust the volume of the microphone. So we actually modulate it in two different places, but it comes out with, once it's modulated, the two signals are mixed. The signaling and the microphone audio are all mixed together. And like I said, like I mentioned last week, the receiver can't tell the difference between direct modulation and phase modulation. The end result is the same. It's just a method of how we do it. Okay, now what I'm going to show you is a thing called a phase lock loop. You know, in years past, if you had a 6-channel radio, you had to have 12 crystals for it. You had to have 6 crystals on the receiver and 6 crystals on the transmitter. So every channel had to have 2 crystals in it. Well, that makes a really big radio. It's a lot of crystals to put in a radio. So the engineers and the scientists have discovered how we can create the frequency with no crystals. Well, actually, just a couple of reference crystals. So I'm going to explain how this works. We start out with, this is called a voltage controlled oscillator, or sometimes called a VCO. Now this whole circuit is called a phase lock loop, or sometimes referred to as a PLL. And then it has a VCO in it. And a lot of people, they don't know the difference, and they kind of interchangeably use one term for the other. But a phase lock loop is the whole circuit, and the VCO is one part of that circuit. So I'm going to show you how that works. So the VCO, or this voltage controlled oscillator, creates the frequency. This is the frequency you're going to transmit over the air, and but it's controlled by a DC voltage, and I'm going to come back to that once we get through the whole circuit. So this is the output frequency. We can send it right into the transmitter, or we can switch and send it in to the mixer for the receiver, because this can actually switch back and forth. So when we're in the transmit mode, it becomes the transmit frequency. When we're in the receive mode, it becomes the mixer frequency. And it's all created by the same circuit. Okay, on this side is where we put in a DC voltage, and that controls the frequency of this oscillator. If the DC voltage increases, the frequency increases. And if the DC voltage decreases, the frequency decreases. So somehow we have to make it so that that DC voltage is very precise, because it's not very much change. Typically, the control voltage runs between about 5 and 7 volts. So you got about a 2-volt range there to cover all the frequencies that you want to talk on. So they're very sensitive, extremely sensitive. So what we're going to do is take this output frequency, and we're going to run it into a buffer amplifier. It's just a small amplifier is all it is. And from there, we're going to go into what's called a divide by circuit. And what it's going to do is it's going to take the frequency coming out of the VCO, and it's going to divide it by some number. And that number is going to be controlled by the microprocessor. So the processor is going to tell it what to divide by. Okay, so that's going to come into here. And then this output frequency is going to be whatever this frequency is divided by whatever the controller said to divide it by. So you might take the output frequency, and we're going to say we're going to divide it by 62.245. So it's going to mathematically divide that frequency down so that the output comes out at a very low frequency. And that's going to feed into this circuit right here. And this circuit is called a comparator. So what it's going to do is it's going to compare this frequency that's coming out of here and this frequency which is being generated by this local oscillator. And this oscillator does not change, it's fixed, and it's only a reference, and it feeds a frequency into here, and this is feeding a frequency into here, and the resulting output is a DC voltage. So what's happening is we take this frequency here, divide it by something, and compare it to that, and the resulting output is going to be a DC voltage. So if this frequency starts to drift a little bit, if the frequency starts going high, it's going to cause this frequency to go high, and it's going to be different from this frequency here, and so it's going to cause the DC voltage to go down lower. And by lowering the DC voltage will cause the VCO to shift the frequency back down. And likewise, if the frequency out here starts getting too low, it's going to cause this frequency here to be low, and it's going to be lower than the frequency here, which is going to cause the output voltage to increase. So this whole circuit, it's we call it a phase lock loop, and it it loops back into itself, and it's continuously adjusting this DC voltage. And this voltage fluctuates constantly, but it fluctuates by only tiny, tiny, minute amounts, probably not even microvolts. The shift is just very small because it keeps this frequency right dead on, and these are very, very accurate. The output frequency is just exactly right on it, and they don't drift. But this is how we create the frequencies. And like I said, this frequency output, we can feed it into the transmitter, and that becomes the transmit frequency. But in the receive mode, we can change this number here and make it feed into the receiver input, or the receiver injection frequency, which is going into the heterodyne circuit. So one VCO controls all the frequencies in the radio, both transmit and receive. And then down here, oops. There we go. So down here, we have a microprocessor. And this microprocessor, when you program your radio, you put in all the numbers for it, and the microprocessor can look at the frequency that you want to, say, receive on, and then it can calculate what it needs to divide by. Oops. Okay, so it will change what it's going to divide by right here so that the frequency comes out what it needs to be over here to be compared. So if you change frequencies, it's going to change the divide by number, which will then shift the frequency out here and cause it to come out different over here. So it's all controlled by this microprocessor. So this is, and now you don't have to know any of this on the test. There's nothing about the VCO or the I'm sorry, the phase lock loop. I got lost there. But I thought this might be of interest to you because this is how almost all radios work in today's world. It's all done by a microprocessor, and it's all controlled with a phase lock loop circuit, which generates the frequency. And if you notice, in today's world, you don't have to set the frequencies. You just program it and away it goes. Because these just don't drift. They don't drift at all. The old times when you used to have to put crystals in, you'd have to periodically retune them and get them back on frequency because the crystals drift a little bit, and but those days are gone now. So that's how we do it in today's world. That's how you're able to just program the radio and it comes out on the right frequency. Okay, here's another question. Just how sensitive is the receiver on a radio? Okay, let me show you. Let's take a typical AAA battery, 1.5 volts, and let's theoretically, let's say we can cut off 1/3 of the battery. Okay, just in theory. So we were going to end up with a 1-volt battery and a 1/2 volt battery. So we don't need the 1/2 volt, so let's just set that aside. Now we're going to take this 1-volt battery and we're going to slice it into 1 million equal slices so that each slice is now 1/1,000,000th of a volt. We call that a microvolt. And now, so that's 0.000001 volts. So now we're going to take one of these slices and we're going to slice that into 10 equal parts. So now each one of those slices is 1/10 of 1/1,000,000th of a volt. And most radios can pick up a signal that small. And that's pretty typical. So the radios are very, very sensitive. They can pick up the smallest, tiniest signals you can even imagine. So there's the actual number for it. So that's and it's all because of that heterodyne circuit that does that. With a preamp and 2 heterodyne circuits, it can make them very, very sensitive. Okay, now I wanted to show you a couple of other things. There's a thing called a squelch control, and a lot of people don't quite know what to do with the squelch control. They know, well, if you turn it one way, you get a static noise, and if you turn it the other way, you don't. And I'm going to demonstrate to you how the squelch circuit works. And there's also a thing called audio muting. There's a term called CTCSS, and I do believe there are questions on that. And there's also another one called CDCSS. And what that stands for is continuous tone coded squelch circuit. And the other one is continuous digital coded squelch circuit. And what we do is we actually put a very low level, low frequency tone on the transmitter. So when you transmit it, and it's very precise, it has to be an exact frequency. And then the receiver at the other end will not receive unless it sees that exact tone. These are used mostly in repeaters. You don't really use them, you don't really need them from radio to radio. Most people just refer to it as a tone, or sometimes called a PL tone. Back in the early days when this first technology first came out, Motorola was kind of the leading edge of that, and they developed this tone system. I think there's like 49 different tones available, and you can program any one of those tones in your radio, and it will produce that exact frequency. And the receiver or the repeater at the other end will not receive unless it sees that exact tone. We do that because, especially for repeaters, because the repeater is up on top of a high mountain or on top of a tall building, and it can hear signals from literally hundreds of miles away. And it might pick up a signal from some city far, far away. You know, somebody talking on the radio, it's going to accidentally key up your repeater because it's so sensitive that it can hear that. So we put the tone on there, that CTCSS tone, so that it will not receive unless it hears that tone. And only our radios have that proper tone in it. So somebody far, far away is not going to have that tone. They might have a different tone, but they won't have the tone that operates our repeater. So that way, our repeater only responds to our local traffic, and it doesn't key up with every little noise that it hears all across the country. And the CDCSS is just a digital form of that. Rather than putting a tone, it actually puts a digital signal. CDCSS isn't as good. It works, but it's not as good as the tone does. But the PL tone is the very most common way of doing it. So I've got a little video here to show you how that signaling works. Let's see, I'll have to pull it up. Let's see. Hope I don't lose this. Keep thinking there's got to be a better way to do this, but I haven't found it yet.
This demonstration.
Okay, so there's the video. Now, gotta bring this back. There we go. Okay, now I think I got it. Should be that one right there, and see if it works.
Okay, for this demonstration, I want to show you what the squelch circuit is for. A lot of people don't quite know what to do with it. If you've got an older style radio or maybe a mobile radio that has a squelch circuit on it, what do we do with that? Well, a radio, when it's in the receive mode, that's what it hears all the time. The radio is constantly hearing noise, and if there's no signal, it just produces noise continuously. And I don't know about you, but I'd get tired of that really quick. About 30 seconds is about all I could handle. So on a receiver, if we listen to the squelch, I'm going to generate a signal. I'm just going to put a tone into it to represent the audio. And as the signal starts to get stronger, it will gradually displace the noise. And you can see how the noise is slowly going away as the signal comes in. And as the signal gets stronger and stronger, the noise gets less and less until eventually there is no noise at all. The signal will completely overcome the noise. So, but we don't want to listen to that while we're waiting for another call. So the radio has a squelch circuit built into it that we can squelch that noise out of there. But when it detects a signal, we can pick up the signal without having to listen to all the noise. Now the squelch is actually adjustable. If you're trying to pick up a signal that's really far away and it's very weak and you're barely able to hear it, then what you do is you open the squelch up. Volume controls. There we go. Okay, so we open the squelch up, and then we turn it until it just barely goes quiet. We very slowly bring it up. So right there, and we stop. We're right on the critical edge so that even the very weakest, noisiest signal will still come through. So as we bring our signal up, okay, see, the signal is noisy, but you can probably still hear. You can still hear somebody talking. So that's for a signal that's very far away and it's very weak. And if you're trying to hear, then you want your squelch right on the critical edge. So it just barely locks up. But on the other hand, if you're talking to a guy that's just down the street, he's blasting through with a very strong signal, then you can tighten the squelch all the way up. And now it won't open until it gets a full, quiet, full, strong signal. So right there is where it opens. So that way you're only hearing the strong signal and you don't have to listen to all the noise. Now in the radio world, once we get, a lot of times if you go over the air and you ask for a signal strength, and somebody will come back and say, oh, you're full quieting. What that means is that your signal is quiet enough that there's absolutely no noise in it at all. That means it's a full quieting signal. In other words, it's a strong signal. But if you hear somebody come back and say, well, you got a little bit of noise in there, that means you're just barely making it. It's very noisy and very weak, but you can still make it out. So you'll hear that over the radio a lot when you ask people, you know, how's my signal? It could be weak and noisy, or it could be full quieting, which means it's a very strong signal. So some radios don't have a squelch control. A lot of the manufacturers it's built right in, and you have no control over it. It is what it is. But some of the older radios, you can still manually adjust the squelch control. And if you're trying to talk to people that are maybe pretty far away and you're not getting a real good signal, having that manual squelch is a helpful thing. If you get one that's factory preset, it's going to be full quieting or nothing. You don't have an option on that. So that's what the squelch control is for, and that's how we use it. But like I say, most radios nowadays don't even have a squelch control, so we don't have to worry about it. You either pick up the signal or you don't. Okay, so let's go back to the classroom now, and we'll talk about a few more things.
Okay. I thought I talked about the CTCSS too, but I guess I didn't.
Well, on these radios, we can turn off the squelch though, even though they don't have a dial for it, right? You can turn it off and monitor the raw signal. Is that correct?
Yes, most radios do have, it's called a monitor button. And if you push the monitor button, it totally disables the squelch control. So you hear all the noise and everything in the background. And so if you're trying to pick up a really weak signal, you can temporarily disable the squelch so that somebody that's coming through really weak and noisy, you could still hear them. Most radios do have that feature. Usually it's a button on the side of the radio if it's a portable. And some radios, the squelch control is programmable. So you can actually go into the programming and you can adjust the squelch. Some of them have that option where you can push a button to adjust the squelch and you can make it up or down. But some of the better radios have that feature.
So Dale, the higher the squelch, or the higher the number on the control, is that more squelch or less?
Yeah, most radios, the 0 on the squelch level is no squelch at all. It's just wide open. You hear all the noise, you hear everything. And as you increase the number 1, 2, 3, 4, and 5, that makes the squelch tighter and tighter. And most of them will go up to about 8 or 10 on the scale. And once you get up to like 10, then it's tight as it'll go, and you're only going to pick up the strong close by signals. But some of them you can actually program them. You can change the squelch setting and lower it down if you want to. Most radios from the factory, they come at about halfway. They're usually set at about 5 on a scale of 0 to 10. So it's, it's not super tight, but it's, fairly tight. So you're not going to pick up any noise off of it.
So when I do a net call, sometimes I can hear net control, but sometimes people will be checking in, and I can't hear them, but I can hear net control responding to them. So in that case, I would want to maybe open up the squelch so that I could hear their signal.
Well, if it's coming through a repeater, that won't help you any, because it's actually the repeater that's not picking it up. But if you're on a simplex channel where you're talking direct radio to radio, then yeah, you can turn the squelch down and maybe pick them out. Some radios have what's called a reverse function. So you can actually reverse the transmit and receive frequencies. So that way you can listen to, if somebody's trying to talk into the repeater, you can actually listen to them direct on the frequency that goes into the repeater. And some people are able to do that. If they can't hear it through the repeater, they can put it in reverse mode and sometimes open the squelch up and be able to pick them up, even though it's a very noisy signal.
So that's kind of almost like a simplex in a way in that regard, right?
Right. Yeah, it basically operates like a simplex. So you're actually listening on the input frequency to the repeater, and if you transmit, you're transmitting on the output frequency. But some radios do have that feature, and some of them do have the programmable squelch where you can adjust it if you want to. And usually it's only the older radios that have a squelch control, an actual dial on it where you can adjust it.
How do you get on simplex?
You program it for simplex. Well, now actually some radios, some of the better radios have it where you can put it on a repeater frequency, and then you can push a button, it'll make it go to simplex on the repeat frequency. That's sometimes an option too. Most of the time you just program your radio with a simplex channel and a repeater channel, and if you want to go to simplex, you just change the dial and go to the simplex channel.
I'll have to get that done.
Okay.
So on a Bofang, you got channel mode and memory mode.
Right.
Okay. And the memory mode, I think, would be where everything is programmed, correct?
Yes, the memory mode is where you have pre-programmed channels and you can't change them. You just select which channel you want to talk on. And if you go into the VC, what's actually called the VCO mode, then you can manually dial in a frequency and talk on that frequency. It's not programmed into your radio, but you can temporarily just transmit and receive on some frequency, whatever you dial in.
So in answer to Sherry's question, how do I get a simplex frequency? So if she wanted to talk on simplex to somebody, she could just go into the channel mode and use the keypad on the Baofeng and actually push the buttons to that correct frequency, right?
Yes, that is true. You can do it that way. Yeah, if you go into that, what they call it, the VCO mode, where you can just manually punch in a frequency and you can talk and listen on that frequency. And then when you go back to the channel mode, you go back to the pre-programmed channels. So some radios do have that feature. Actually, quite a few of them do. Okay, any other questions or thoughts?
Darn good class there, Dale.
Oh, well, thank you.
I learned a lot from this one. Thank you.
Yeah, there isn't a lot on the test about it, but some of the there are some test questions where they show a block diagram, and it asks you, what does this block represent? I think the diagram that I saw had the receiver with the heterodyne, the preamp, and the antenna, and the local oscillator, and it pointed to this block and says, okay, what is that block? Well, that's either the mixer or the heterodyne, whatever you want to call it. Just being able to identify it, that's all there is to it. Anyway, I thought that might be interesting just to kind of see, well, how does this thing work? How does it do, what I'm trying to do? And there's no magic involved. It's all scientifically engineered to do what it does. And scientists have been working for years and years and years and years to develop all of this. It's come a long way since the early days.
But if you're not a scientist, it is magic.
Yeah, that's true. To the rest of us, it's just magic. When I was going to school, we sometimes referred to it as the black box theory. We got this black box. I don't know how it works. You put a signal here and somebody hears it over there. Sometimes that's the only way we can explain it. Okay, so the homework assignment for this week is Chapter 5, Amateur Radio Equipment. And that should be a fairly easy chapter. It just talks about all the different kinds of equipment, kinds of radios, kinds of antennas, and so forth. And then in the following weeks, we'll start getting into some of the stuff we've already talked about. And so hopefully by then it'll be familiar to you. Okay, any other questions or thoughts?
Thank you, Dad.
Okay, well, thank you. And that's all I have for tonight. And like I say, I'll send out the video. Well, actually, let me stop the recording.
Thank you.
Stop recording.